Hello, and welcome to the TI Precision Labs lecture discussing the basics of analog input 2-wire 4 to 20 milliamp transmitters. These types of transmitters use a current input that's translated to the 4 to 20 milliamp output signal. The concepts introduced in this presentation will be described using a mix of discrete solutions and partially integrated solutions using TI's XTR products. In this video, we will derive the transfer function for a 2-wire transmitter, introduce an analog front-end design for an XTR116, and go through the design considerations for a 2-wire transmitter such as the 4 milliamp current budget, I-return pin, and compliance voltage. In a previous video, we introduced the following characteristics of a 2-wire 4 to 20 milliamp transmitter. To summarize, a 2-wire transmitter uses 2 wires to create a loop that transmits the signal current and supply current to power the transmitter. The transmitter can supply power to the sensor and its input circuitry, but these voltage levels all float with respect to the transmitter return, I-return. The next few slides will derive the transfer function for a 2-wire transmitter, as well as explain why I-return cannot be grounded to the loop supply, ground, or any other earth ground, and why the transmitter, sensor, and input circuitry must consume less than 4 milliamps. This example will walk through the derivation of the transfer function for this standard 2-wire current loop transmitter topology, which is the circuitry featured in the XTR115, 116, and 117. First, negative feedback sets V plus and V minus of the op-amp equal to each other. V minus is tied to I-return, so V plus will be equal to I-return as well. With V plus set to I-return, the current inputs to the system across the R input and R offset resistors can be determined based on the V DAC and V reg voltages. We can assume no current goes into the op-amp, and therefore the current through R1 is IN, the sum of the input current from the DAC and the offset current. The voltage drop across R1 and R2 must be equal in order to set V plus and V minus to the same voltage. The op-amp will control the BJT to produce the remaining required output current. The quiescent and active currents for all of the devices in the circuit flow back through the 2-wire I-return pin. These currents, plus the current through the BJT, sum and flow through R2. This sum can be defined based on IN in the ratio of R1 and R2. The output current, Iout, equals IN plus I-return plus IBJT. Combining these equations gives us the final transfer function, which is based on the values of VDAC over RN, VREG over R offset, and R1 over R2. The TI XTR116 2-wire 4 to 20 milliamp transmitter used in this example is a current input, current output transmitter. Other transmitters may use a voltage input or a digital input like the fully integrated transmitters introduced earlier in this series. The on-chip regulator and reference can supply the power for the input circuitry. All of the returns are tied together at I-return. The output of the input circuitry is connected to the IN pin of the XTR. This input circuitry can perform any of the required conditioning that the sensor needs. In this case, an INA333 with a reference of 500 millivolts, created from the XTR116's precision reference, is used to amplify the differential voltage across the bridge. A resistor at the output of the INA333 translates this voltage into a current. The transmitter input signal can also be supplied directly from a current output DAC or a voltage output DAC with a resistor at the output. As we saw in the derivation slide, the current gain of the transmitter is set by the internal resistors of the device. If the gain of the transmitter is different than 1, the input current needs to be scaled correctly in order to get the correct 4 to 20 milliamp at the output. The gain of the XTR116, for example, is set to 100 by R1 and R2. This means the input current needs to be scaled to 40 to 200 microamps. Depending on the output range of your sensor, you can add a resistor from the 4.096 volt reference to IN to create a current offset. For example, if the sensor outputs a value of 0 to 4 volts and the input resistor is 25 kiloohms, the current input to the transmitter would be 0 to 160 microamps. Adding a 102.4 kiloohm offset resistor will add 40 microamps of current, which will bring the input to the correct 40 to 200 microamp input range. In the next few slides, we will talk about the importance of the I-return pin, the total current consumption of the input circuitry, and the compliance voltage of the loop. As mentioned previously, an important thing to note when using 2-wire 4 to 20 milliamp transmitters is that the I-return signal can be used as a local ground, but the voltage on that pin needs to float. The regulator, reference, and input circuitry also float at the potential of I-return. iReturn cannot be connected to the ground of V-loop or any other external power supplies on the sensor side. Depending on the currents in the device, the iReturn node will have a varying voltage level. If this is grounded, the voltage level will not be able to fluctuate and provide the correct current outputs. Let's go through some examples using the equations we derived earlier. This example will use an ideal current source for the input to the transmitter. If the current source is set to 0 amps, and an offset current of 40 microamps is sourced from the reference, the total current input to the transmitter is 40 microamps. The voltage level at the iReturn pin is the sum of the voltage across the R2 resistor and the load. To get the voltage level across the R2 resistor, multiply IN by R1 to get 0.099 volts. If we have a 250 ohm load at the output of the transmitter, we can calculate the voltage at the load. Based on the transfer function derived earlier, an input current of 40 microamps will give an output of 4 milliamps. To calculate the voltage across our load, we multiply 4 milliamps by 250 ohms to get 1 volt. This means that the voltage at iReturn referred to ground is 1.099 volts. If the current source is increased to 160 microamps and an offset current of 40 microamps is sourced from the reference, the total current input to the transmitter is now 200 microamps. To get the voltage level across R2, multiply IN by R1 to get 0.495 volts. With the 250 ohm load and a 20 milliamp output of the transmitter, we can calculate the voltage at the load by multiplying 20 milliamps by 250 ohms to get 5 volts. The voltage at iReturn referred to ground is 5.495 volts. The next few slides will go over the compliance voltage of a 2-wire transmitter. The compliance voltage of a 2-wire transmitter needs to be met so that the regulator can supply enough voltage to power the op-amp. Without a functioning op-amp, the transmitter is no longer able to regulate the output current. As seen in the example on the previous slide, the voltage at the iReturn pin reached 5.495 volts. The compliance voltage is set so that the iReturn voltage can't rise too close to the supply voltage of the transmitter and cause the regulator to turn off. The XTR devices have a specified compliance voltage given in the datasheet. An important thing to note is that the V-loop voltage needs to be greater than the compliance voltage. This will be explained on the next slide. The XTR116 has a minimum compliance voltage of 7.5 volts. The voltage seen at the V+ input of the transmitter is not equal to the V-loop voltage. This is because the voltage drop across the load and resistive losses in the cables cause the V-loop supply to decrease. The loop supply needs to be at least V compliance plus I out max times R max. The I out max of a 4 to 20 milliamp transmitter is 20 milliamps, and R max is the sum of your load and cable resistance. Common voltage compliance issues come from long wiring distances, poor quality wires, multiple receivers, and a load that is too large. When testing, make sure the correct resistor value is loose for the load. If the compliance voltage is not met, the output current of the transmitter will stop increasing. In the example here, there is a load resistance of 500 ohms and a total wiring resistance of 400 ohms. Multiplying this by the 20 milliamp max output current and then subtracting from the loop supply voltage, only 6 volts is left across the transmitter, which is below the specified compliance voltage. To fix this, the supplies can be raised or the load and wiring resistance can be lowered. The equation can be arranged to solve for the max resistance allowed for a 24 volt supply, which results in a max resistance of 825 ohms. This diagram shows the current flow in an XTR116 2-wire transmitter. As discussed earlier, the output current I/O is the sum of iReturn, IN, and IBJT currents. IN and IBJT will always be positive currents. This means that iReturn needs to be less than 4 milliamps in order for the output current sum to reach the lower bound of the 4 to 20 milliamp transmission. For example, if iReturn totaled to 5 milliamps, the minimum output of the transmitter is 5 milliamps, even if IN is 0 amps. The XTR116 shown has a maximum quiescent current over temperature of 250 microamps. This leaves 3.75 milliamps of current for the remaining circuitry powered by VREG and VREF. Using lower resistance bridges or internal parts with high supply currents are common reasons for iReturn to be greater than 4 milliamps. Input isolation is necessary if multiple 2-wire transmitters need to be connected in parallel. As seen in a previous video, multiple transmitters connected to the outputs of one multi-channel digital to analog converter will create conflict between the iReturn pins of the transmitters. The voltage at the iReturn pins needs to flow in order to produce the correct current output. So if multiple iReturns are tied directly to one ground pin of a digital to analog converter, they will not be able to flow at the correct voltage. In this example, 2 sensors are fed into one microcontroller. The data from these sensors is sent out to the 2-wire transmitters through 2 digital to analog converters. The problem here is that the iReturns of the transmitters are shared at the microcontroller. If the first digital to analog converter was trying to output a value corresponding to 4 milliamps, and the second digital to analog converter was trying to output a value corresponding to 20 milliamps, the iReturn pins of each transmitter should flow at about 1.1 volts and 5.5 volts respectively. With the iReturn pins tied together to the ground pin of the microcontroller, as seen in the diagram, the iReturn pins will not be able to flow independently to provide the correct current output. TI offers a digital isolation solution that would allow this design to work with 2-wire transmitters. A digital isolator such as the ISO 7330 is placed between the microcontroller and the digital to analog converters. Each digital to analog converter is individually supplied by the voltage regulator of its transmitter. The microcontroller is supplied by an isolated supply created from the voltage regulator of one of the transmitters. Because of this, the voltage inputs to the 2-wire transmitters are allowed to flow as needed for each transmitter to regulate the correct current output. Input isolation can also be used if you want to supply a sensor with an independent supply. This is useful if the sensor and its input circuitry use more than 4 milliamps of current. The current for the sensor and input circuitry will come directly from the independent supply, and the digital isolation separates the input circuitry from the transmitter. In this example, only the 2 digital to analog converters are supplied from the regulators of the XTR116s. This slide shows a table of TI's 2-wire XTR 4 to 20 milliamp transmitters. As you can see, the XTR115 and 116 have external voltage references in addition to the internal 5-volt voltage regulator. The XTR101 provides dual-matched precision current references that can be used to excite RTDs or bridge sensors. Along with the general-purpose XTRs, we also have specialized RTD and bridge conditioners that will be shown on the next slide. Along with the general-purpose 2-wire transmitters shown on the last slide, TI also offers specialized RTD and bridge conditioners. They contain built-in linearization correction to correct second-order sensor nonlinearities by controlling the excitation voltage or current supplied to the sensor. That concludes this video discussing the basics of 2-wire transmitters. In the next video, we will dive deeper into 3-wire transmitter topics. Please try the quiz to check your understanding of this video's content.